My name's Frank Buzzard. Some say Buzzard. I tell them Buzzards are the rich ones. I'm plain old Buzzard. And it's an honor to be here. I'm glad you're here. I'm glad you're continuing to work on the space program. And I want to tell you a few things that I learned about the Space Shuttle and a little bit about the space station. So we'll just jump right in here. It's a great song. I won't try to sing it. I have been known to do that in public before, but a little choked up here, so I don't want to mess it up. Where it began, I don't begin to know it, but then I know it's growing strong. And one of the important lessons learned for you in this room is stand on the shoulders of giants. All of us have done it. Learn from what they did and extend the successes that they had. And as we go to the next programs within NASA, be very aware that you want to learn and use and extend and grow the systems that work. Because every time you go to a new system, you're going to find things that don't work. It's easy to draw a rocket engine on a view graph, but nobody flies a rocket engine, like Jody told you, until they go test it on a test stand. And they always find things that aren't right. We had a nation with bold leadership. We had the will to succeed, and we chose to excel in space. We chose to do that. Don't forget that. We had a NASA and industry team, clear goal and objective. We had a vision to go to the moon, and we did it. We built human spaceflight core competencies in design, test, and operations and infrastructure, and those are the things that you want to build on for your next systems. It was a huge investment. We learned huge lessons. Listen to what Russ told you about the things that we learned here at the Kennedy Space Center. It's very important as you go to the next systems not to start over, build on the shoulders of the giants that have preceded us. Apollo changed the world forever. That view from Apollo 8 changed our vision of this world. And then we went to the moon several times with great hardware. We built an ops team. We actually learned to go to another planet. And my challenge to you is to go do that again. The next obvious planet is Mars. We may and probably should go to the moon to learn how to get there, but don't forget that Mars is where we really need to go. Then we dreamed of a reusable space plane. Why reusable? We wanted to reduce cost. And what did we want to do with that space plane? We wanted to get to low Earth orbit without throwing things away, so that we could build the next transportation node or infrastructure, and that was the space station. And the purpose of the space station was to be like St. Louis when we expanded west to go to Mars. And Mr. Nixon and James Fletcher announced that in 1972, and so that's what we set about. Tom Hosier talked about early space shuttle concepts. The initial designs were intended to be fully reusable. Budget constraints and reality led to this design that you see flying today. And it is really the most remarkable spacecraft, aircraft, or flying system that has ever been designed by mankind. We had some tremendous challenges to overcome, not all of them technical, some of them just big. Building at Marshall, we built the structures and materials. We tested a full-scale tank. We simulated the orbiter aft structure. We had to shake it and bake it and roll it and make sure we understood our structural margins. The external tank is like the spine of your human body, and we had to understand that it could take the aerodynamic loads. The solid rocket boosters are attached to it. The orbiter is attached to it. So all of those things that make lots of fire and smoke and tremendous loads, including the air that we fly through, have to be reacted by this entire integrated structure. Kennedy had to build new and modified launch and landing facilities. They built on the materials that we used from Apollo. They used what we could. They modified and built new things that we needed, the orbiter processing facility, the SRB checkout, the RPS facilities to bring them here by train, and the external tank by its barge. It comes all the way from Nolens. It's hard for me to say that, not being born there, but that's Nolens. It's not New Orleans. And so Kennedy built all that. JSC did the mission operations, crew training, orbiter systems with the life support, fail-op, fail-safe avionics. Our avionics design was full fly-by-wire. I have to tell you a little story. The Space Shuttle main engine provided the umbrella. I grew up in guidance, navigation, flight control, avionics systems, the computers, moved through all of that stuff later into program and system engineering. And without the main engine, having 10 engines blow up that Jody talked to you about, and taking 95 starts to get to half power, and being 2 years late, our avionics system would not have made 1979. It took us a tremendous amount of work just to get 4 computers to talk to each other and stay in the system and stay in synchronization and understand that the information that they were sharing was always the same information. It took a very long time. So we thank you, Jody, and the Marshall Elements for providing this cover for the rest of the system. So don't ever think that it was the propulsion system. It was the whole system was really difficult, the thermal protection system, getting our control centers. And we, as Tom Mosier said, we traded time for the budget that we had, but we made it work. And of course, Stennis is where we do our engine testing and certification testing. And don't forget what I told you, it's easy to draw a turbo pump on a view graph or a main engine on a view graph, but they never work like the view graph says. You gotta test them. I worked in the Mission Control Center's guidance support. And after we landed on April the 14th, I was about 10-foot hover. And Jim I. Anson came out and I said, it worked. The damn thing worked. Couldn't believe it. Picture Jim and his wife. He was a World War II bomber pilot, B-17 pilot in the Pacific. Our crew, keys to success. We had a clear objective. We had a common goal. We divided our labor where we had our strengths and our core competencies. We did propulsion at Marshall. We did launch and landing at Kennedy. We did mission operations crew training in Houston. We did engine testing at Stennis. Tom talked about something that's very important. We kept the interfaces simple, and we had engineering excellence, outstanding people, facilities, tools, and budget. It was limited, but we made it do the work. We had to build multi-center relationships with our centers and contractors. Acceptance of a better idea is not a strength, is a strength, it's not a weakness. I think of Apollo, when the initial going to the moon involved an Earth orbit rendezvous, and we didn't have a large enough launch vehicle to do that. And a group of engineers from Houston went to Marshall and said that we can do this with one Saturn V. If we do a lunar orbit rendezvous, we have enough performance to do this. It was considered very dangerous, but Wernher von Braun, who was working on the Nova rocket, which was even bigger than a Saturn V, realized that we had to take that risk and do that in order to fly this mission with one. And even though the idea came from Houston, von Braun and his team at Marshall accepted it, embraced it. It was a long fight, a couple years, but they went forward and we executed that mission. So that was a strength, not a weakness. Lead from the front, communicate, communicate, and communicate. One of the early people that I worked for in the avionics was Howard Tyndall. He would send out Tyndallgrams, And his tyndallgrams were ways to keep us all informed, make sure we understood the problems. Were we on the same page? Were we all working on the same issues? So communicate, communicate, communicate. Attitudes to avoid are human nature, in a simple way of saying it. First is arrogance, guilty. Ego, guilty. Ask my family. Organizational, I'm in charge, I know it all. Organizational stovepipes. We tend to only talk to people that we work with. You really have to work hard to go outside your organization to build the relationships at other centers with other people. Fellow you're going to talk to here later, Harold Ross, went to Moscow with me, and we helped try to figure out what was wrong with the solid fuel oxygen generator that caught on fire on the Mir space station and caused nearly a terrible fire and almost our loss of our crew. And I knew where to ask. I needed somebody who knew something about combustion in zero G. So you've got to reach out, know where your talent is, and then go ask for that help at other centers. It's key. Don't restrict or suppress the flow of information. Never belittle an opposing view or conflicting view. One thing I learned on the International Space Station was, and this was key, I took a course on different cultures. And we tend to view cultures from our own prism of experience, but other people have different cultures, and it's okay. And the key thing is to understand what's different, accept that it's different, and then just, that's really a strength. It's not a difference. Different is okay. We think differently and talk differently at Marshall than we do at Johnson, than we do at Kennedy. It's okay. Just like Jody says, all of y'all. That's plural in the South. I'm a Yankee. I was born in Pennsylvania, grew up in Colorado. I had no idea. Why would you say all of y'all? And now I actually say it too, so it's okay. A couple of unique capabilities about Shuttle, and what I wanted to do was be visual, not preachy. So I want to tell you a couple of things that are unique about Shuttle. Shuttle was designed as a living quarters for learning to work in space and to learn to repair things and build things in space. Its mission was intended to build the space station, which we did, and we could not have built the space station without the shuttle. So something to remember, if you're going to build other structures in space, you need an ability to go out to space. You need an airlock. We had an airlock in the shuttle. You need robotics, so you can grab things and hold them and work on them. You need the capability to support your crews so that they have to have spacesuits. And since we are retiring the space shuttle, we're losing some key capabilities of building future things in space. So now the place that you have to build things in space is going to be the International Space Station. It has power, it has robotics, it has life support, and it has an airlock, and it has spacesuits so you can go outside. You can take a crew in a capsule, but you probably can't build things in space from a capsule. It's okay as long as you have a place for where you're going next, that you have these capabilities that you can build and service large structures in space. Another unique one on on Shuttle was it can return payloads. And we are giving up that capability. The Soyuz can bring back about water cans full of things from the space station. So if we actually do learn to grow things in space that are useful, like crystals that are 1,000 times bigger than things we can grow on Earth and make giant supercomputers for them, if we can make vaccines that can only be made in space, you have to have a way to get them back here. So any follow-on vehicles need to have some payload return capability. The Other unique thing about Shuttle was we designed it, along with several of its payloads I'll talk about here in a second, to be serviced and repaired. Hubble is one of those. We'll talk about Hubble in a second. But with this fundamental capability of having people be able to go outside, a cargo bay, a work area in space, we found that we were able to expand our capabilities by actually retrieving satellites. We brought some back, and we repaired some in orbit that later became successful. So let's talk about a couple of those. First one, Bob Crippen and his crew. George Pinky Nelson attempted to capture the Solar Max in 1984. He flew out there with a backpack, and we had designed this fancy tool on the front of Pinky that was supposed to grab these pins. We had drawings of these pins, and these pins looked like a good thing that we could design this tool to grab. He goes out there and bangs into the spacecraft, and that pin didn't match the drawing. It had some interference, and his capture device didn't work. That came back to bite us later, so you got to keep it simple, keep the interfaces simple. The way we actually grabbed this thing was, we were lucky. It was designed to be captured and repaired by the shuttle, and it had the fixture that we could grab it with the Canadian arm from the Space Shuttle. They stabilized the satellite. The next day, Bob Crippen came back, and he grabbed that satellite, and we put it in the cargo bay and fixed it. And so that's another example of how the ops team saved the engineering teams. And it's critical that you really do understand your interfaces, and don't be surprised if your drawings and your documentation isn't really up to snuff. And that turned out very well. We repaired it. Another one were 2 commercial satellites. We had a problem during this time frame in middle 1980s, where our booster rocket, it was a solid rocket device, on the back of these satellites that's intended to send it up to geosynchronous orbit, had a generic problem, and we left these 2 very expensive communication satellites in low Earth orbit. We were able to go up and get them. Dale Gardner, we designed a new tool that had to go in the back of this rocket engine that wouldn't work, and his tool slid into the nozzle and captured the nozzle, and he's on the manned maneuvering unit, and he brings it back, and he and Joe Allen take that and put that in the cargo bay. We actually recovered 2 satellites on that mission. Both had the same problem, and we brought them back, and we repaired them on the ground, and they launched on a later expendable rocket. Pretty amazing stuff. None of this was a planned capability for the shuttle. So we had to use some innovation. We had to build some new tools, and we actually trained and sent the team up there, and they were very successful. STS-49, first flight of Endeavour, first flight of a new operational increment. I want to talk just a bit about better is the enemy of good enough. Tom Mosier talked about that. I just added a word. Better is the enemy of good enough. On this mission, we went to get the Intelsat 6. We built this fancy tool to grab it in the back, and here's Pierre Thiaud out on the end of the shuttle's arm trying to grab this satellite, and the brakes on the remote manipulator, or the Canadian arm, kept coming on. And that was very distressing for the crew who's trying to maneuver him out there, and so they would reset the brakes and etc. Well, it turns out that I was the chairman of the Shuttle Avionics Software Control Board, who approved a change that our engineering team said we have to tighten up our protection for a possible runaway robotic arm. If that robotic arm runs away, it's going to bang into something and hurt something. So I approved a software change that tightened up the limits, but we weren't able to test that change with all of the robotic arms. And the first test with the hardware was on this mission in orbit, and for that particular arm, the software thought the arm was running away. It was working just fine. We just had the limits too tight. Better is the enemy of good enough. The other thing we did was and I grew up in this world, Lambert Guidance Rendezvous. the engineers came to me and said, we have this possibility that we can have a numerical instability in Lambert guidance. Lambert guidance is what we use for the onboard targeting. And on the third rendezvous attempt, after we had failed to capture this satellite and we had one more chance, the Lambert guidance routine blew up because it was iterating between two limits and it wouldn't converge and give us the answer. Well, the ground team was able to finish the rendezvous by targeting those burns from the ground and using an alternate burn system that we called PEG 7. So they saved me on that one. What did I learn? I said, you better do a darn good job of assessing the risk of the change that you're trying to make, that's trying to make it better, to make sure that you're really solving a problem that needs to be solved. And then be careful that you don't introduce unintended consequences. You really need to quantify the risk, make sure that you're working on the problem that needs to be worked on. Then the crew had to grab this thing outside. Dan Brandenstein did the best formation flying of any pilot I've ever seen in my life. And the three guys went out there, first three-man EVA, grabbed this satellite. Brandenstein had a terrible headache because he worked so hard to execute this thing afterwards. And then they put the capture arm, and we repaired this and put it back in service. We launched NASA's great observatory. Spitzer was launched on an expendable. Hubble spacecraft, another thing that changed our view of the world. We had 5 repair missions. It was designed from the beginning to be serviced by the shuttle. Its instruments upgraded by the shuttle. We replaced failed instruments. We added new capabilities. We reboosted it. And Hubble is still working to this day. And Hubble has changed our view of the world. Now, because we didn't spend enough money to test the main mirror, here's the first picture Hubble took of the Whirlpool galaxy. That was not a good day. So our Goddard team got together and they put eyeglasses on Hubble. And now Hubble, with this flawed main mirror, has done an extraordinary job. We found out that when these solar panels went into light and dark, they would flex and they would cause the spacecraft to jiggle, and that affected Hubble's view. So on one of those repair missions, we changed the solar panels. This is a view of a piece of sky in the Fornax galaxy that's like looking through a straw, 1/10 the diameter of the moon when we look at it from the Earth. It's all black. But out there in that universe is an amazing creation. So just think about that. Andromeda, 1924, Edwin Hubble found a yardstick. We didn't realize Andromeda was outside of our galaxy until 1924. And the Hubble telescope is named for Edwin Hubble, who found a star that we knew its luminosity, and called a Cepheid variable. And when we found this star, we could measure how far away this place was. 2.5 million light years away. I think the Chinese must have seen some of these because they look like they're, what are the things we launch, 4th of July? Those are stars. Some of the iron in our blood came from exploding stars in our region that our sun later came from. Most of the beginning of the universe was hydrogen and helium. Most of the heavy elements that you see, including the iron in our hemoglobin, came from these exploding stars. We paid a terrible price, but we kept going. We made some needed changes. These are examples of better was not the enemy of good enough. We have the best solid rocket motor design. We designed new APUs. We put new brakes, put new tires, drag chutes, block changes. We have the best reusable rocket engine on the planet. External tank allowed us to build the ISS. So there are, as you fly new systems, you will learn. You will need to change them. Be careful that you're working on the right risk. And the improvement process, the other thing I've learned is be very careful of design deficiencies that you think you completely understand. Our computer models do not model the entire real world. We thought we understood O-rings and that we had enough margin and enough safety, but we didn't understand how that O-ring would work in a very cold environment. We thought foam was not a danger, but was a maintenance issue. But foam hitting at 500 miles an hour on the wing, we paid a terrible price for. Challenge the test data and the modeling. Don't believe everything a computer tells you. Have a healthy skepticism. Turbopumps that turn at 35,000 RPM, we designed those blades not to have cracks in them. When you see cracks, be careful, thinking that you understand crack propagation at minus 428 degrees Fahrenheit, spinning at 35,000 RPM. I talked about better's the enemy of good enough, a quantitative risk assessment. There are several ways to do this. Try to quantify that risk. Make sure you're working on the risky problem, the one that's likely to get you, and make sure that your fix is going to actually help reduce the risk. And then make sure you're very careful that you've assessed unintended consequences. And be aware you can't be 100% sure and correct. Then we used the shuttle to learn how to build space stations. This is Shuttle Mir, how to work with the Russians. We were late, but we did exactly what we intended to do with the shuttle. We built a remarkable laboratory and a working environment to learn to live and work in space. And I think the space station should be the St. Louis of where you go next, because that's where we outfitted and prepared the wagon trains to go west, a transportation node. And there she is. 16 nations working together. It was an awesome challenge, but what a goal. Make sure you have fun along the way. Some things are better left in the ocean than eaten. This place right here is important for the last site. This is where the Japanese launched their facilities, a little island south and east of Honshu at Tanegashima. And some parting thoughts. Let me start at the bottom. Are we going to go the way of Portugal? The Portuguese, Henry the Navigator, made unique hull designs and ships, sail designs. They were leaders in exploration for 150 years. In 1543, the Portuguese landed on that island of Tanegashima and introduced modern weapons, guns, to the Japanese. It changed their culture. 150 years, then they left exploration and they ceded that to Spain, England, and the Dutch. So think about that carefully. Are we going to lead in space, or are we going to buy seats from somebody else to go to our space station? That's a way of commercializing space. I would just like to see us buy our own seats from a commercial provider, but those are the choices that we've made. Commercial transportation is going to be very important. The railroad industry built the railroads. The government was a partner. They guaranteed bonds. They were a good customer. They gave the railroads land, but the railroad industry built and operated the railroads. Aviation industry built and operated commercial aviation. The government role was very important, did research and development, spent a lot of money streamlining airplanes. The war accelerated that because we had to have them. But the aviation industry built airplanes and operates to this day the commercial industry. So we should ask ourselves, is it NASA's job to build and operate new rockets, or should NASA work on technology development, nuclear propulsion for anything that you want to do between planets or your transportation node? If I want to go to the moon and Mars, maybe I should start at the space station and use a nuclear rocket to go between them instead of chemical rockets. NASA needs to do the lunar and Mars habitat work, living and working and technology development. It's time and it's hard, it's our human nature. But we have to move from NASA designing and building new rockets and operating new rockets. The satellite industry right now can go to a commercial provider and buy a rocket. And we need to think about that model. There is a proper role for government, but it's time to transition to let the commercial industry take us to the low Earth orbit. And the last one, future space exploration will and should be international, and that's a great legacy of both the shuttle program with the Canada arm and the International Space Station. I thank you.